Bismillahirrahmanirrahim. Assalamu alaikum. Integrating factors. There are differential equations which are not exact, but when we multiply them with some particular type of functions, they become exact. Those functions are called integrating factors. Let us explain it by starting from the previous lecture. If we are given a differential equation of the form m dx plus n dy is equal to 0, and if we partially differentiate m with respect to y and n with respect to x, and they are equal, then we know that equation 1 is called an exact ordinary differential equation. And in that case, the solution of equation 1 can be obtained by integrating m dx, keeping y is constant, plus integration of only those terms of n which are free from x dy is equal to c. Now look at once again. If I have a differential equation m dx plus n dy, the coefficient of dx is called m, and the coefficient of dy is called n. Let us change it by m cap, and I say this is n cap. So the coefficient of dx is called m. In this case, m is equal to m cap and n is equal to n cap. Now if I differentiate m partially with respect to y and n partially with respect to x, and they are not equal, we will say that equation 3 is not exact. Now if we multiply equation 3 with some particular function, let us say f, then I get f m cap dx plus f n cap dy is equal to 0. In this case, m is the coefficient of dx and n is the coefficient of dy. And if I find now that m dy is equal to n dx, in that case we say that 4 is exact ordinary differential equation, and the function f is called an integrating factor. So the main purpose of integrating factor is that it converts a non-exact differential equation into an exact differential equation. In this lecture, we shall study 4 cases or 4 rules to find f. To find integrating factor, let us study rule number 1. Rule number 1 is if my minus nx divided by n is equal to p of x. P of x means it is a function of x only. P is a function of only x. There will be no y. In that case, integrating factor for this differential equation is given by f is equal to e integration of p of x dx. So this is integrating factor for this differential equation. Rule number 2. Rule number 2 is if nx minus my divided by m is equal to q of y. Q of y means it is a function of only y. Q is a function of only y. There will be no x. In that case, integrating factor for this differential equation is given by f is equal to e power integration of q of y dy. That will be the required integrating factor for that differential equation. Question number 1. Solve the differential equation number 1. Here the coefficient of dx is m, which is equal to x square plus x minus y, and the coefficient of dy is n, so n is equal to x. Let us differentiate m with respect to y, we get minus 1, and let us differentiate n with respect to x, we get 1. So we can see that my is not equal to nx, and this implies that 1 is not exact. So we need an integrating factor to convert this differential equation into an exact differential equation. Let us use rule number 1. Rule number 1 is my minus nx divided by n must be equal to a function of x only. So let us put values. My is minus 1 and nx is 1 divided by n, which is x. So this is equal to minus 2 divided by x, and we can see that this is a function of x only. So integrating factor for this problem is f is equal to e power p of x dx. Let us put values. We get e power integration of minus 2 divided by x dx. If we take minus 2 as common outside from integration, we get e power integration of 1 over x is ln x. And here we have minus 2. So this can be written as e power ln x power minus 2. So ln will cancel with e. So integrating factor f is equal to x power minus 2, which can be written as 1 over x square. That is the required integrating factor for equation number 1. Now multiply equation 1 with integrating factor, which is 1 over x square. We get that multiplying x square with 1 over x, we get 1 plus 1 over x and minus y divided by x square into dx plus 1 over x dy is equal to 0. Now equation number 2 will be automatically an exact differential equation. Let us confirm this. Here the coefficient of dx is 1 plus 1 over x minus y divided by x square. So if I differentiate m partially with respect to y, I get minus 1 over x square. And the coefficient of dy is called n, which is 1 over x. So if I partially differentiate n with respect to x, I get minus 1 over x square. And here we can see that my is equal to nx, which implies that equation 2 is an exact ordinary differential equation. So now we can use the formula integration of m dx keeping y is constant plus integration of only those terms of n which are free from x into dy is equal to c. Let us put values in this formula. We get the value of m here is 1 plus 1 over x minus y divided by x square dx. Here y will be considered as a constant, and plus those terms of n which are free from x. So we can see there is no term of n which is free from x. So that term, this is 0, equal to c. Now let us integrate this with respect to x. So we have x plus ln x minus, now y will be considered as a constant. So if I integrate 1 over x square, I will get y over x is equal to c. And that is the required solution for this problem. Question 2. Solve the ordinary differential equation number 1. Here again the coefficient of dx is called m, which is equal to xy square plus y, and the coefficient of dy is called n, which is equal to minus x. Let us differentiate m partially with respect to y. We get 2xy plus 1, and let us differentiate n with respect to x. We get minus 1. Now let us use rule number 2. Rule number 2 is nx minus my divided by m must be equal to a function of only y. So let us put values. We get 2, okay, minus 1 minus 2xy minus 1 divided by m. So m is xy square plus y. Let us simplify this. By simplification, here we get minus 2xy minus 2 and divided by xy square plus y. Let us take minus 2 as common. So we have xy minus plus 1 divided by, taking y as common, we have xy plus 1. Now xy plus 1 will cancel, and this is equal to minus 2 divided by y, which is a function of only y. So integrating factor for this problem is f is equal to e power integration of q of y dy, which is equal to e power integration of minus 2 divided by y dy. Taking minus 2 as common and integrating 1 over y, we get e power minus 2 ln y, which can be written as e power ln y power minus 2. Ln will cancel with e, so we get integrating factor which is equal to 1 over y square. That is the integrating factor for problem number 1. Let us multiply 1 with this integrating factor, so it will become an exact differential equation. So we have x plus 1 over y dx minus x divided by y square dy is equal to 0. Now 2 will be automatically an exact differential equation. Let us check that. Here m is the coefficient of dx, which is equal to x plus 1 over y. So if I differentiate m with respect to y partially, I get minus 1 over y square. And here the coefficient of dy is n, which is equal to minus x divided by y square. Let us partially differentiate n with respect to x. We get minus 1 over y square. So we can see that my is equal to nx. And this implies that equation 2 is exact. So now we can use the formula integration of m dx keeping y is constant plus integration of only those terms of n with no x dy is equal to c. Let us put values. So the value of m is x plus 1 over y dx, keeping y is constant, plus those terms of n which are free from x. There is no term of n which is free from x. So this is 0, is equal to c. Let us integrate the first term with respect to x. We have x square divided by 2 plus integration of second term is x divided by y is equal to c. And that is the required solution for this problem. Rule number 3. If the differential equation m dx plus n dy is equal to 0, is homogeneous, and if I multiply m with x plus n with y, and this is not equal to 0, then integrating factor for this problem is given by f is equal to 1 over xm plus yn. That will be the required integrating factor for this problem. To solve question number 3, we can see that equation number 1 is homogeneous because the power of variables in each term is same. So here the coefficient of dx is m, which is equal to x square y minus 2xy square, and the coefficient of dy, that is n, which is equal to minus x cube plus 3x square y. Now let us partially differentiate m with respect to y. We have x square minus 4xy. And now let us partially differentiate n with respect to x. We have minus 3x square plus 6xy. And we can see that my is not equal to nx, which implies that equation 1 is not exact. Now let us multiply m with x plus n with y and simplify this. So if I multiply m with x, I get x cube y minus 2x square y square. If I multiply n with y, I get minus x cube y plus 3x square y square. Now these two terms will be cancelled and we get that this is equal to x square y square, which is not equal to 0. So we can see that equation number 1 is homogeneous and xm plus yn is not equal to 0. That is why we can use rule number 3. According to this rule, integrating factor for this problem is given by f is equal to 1 over xm plus yn. Let us put values. We have f is equal to 1 over x square y square, and that is the required integrating factor for this problem. Now let us multiply equation 1 with integrating factor, which is x square y square. This implies that we can get 1 over y minus 2 over x into dx minus x over y square minus 3 over y dy is equal to 0. Now this equation number 2 will be automatically an exact differential equation, but let us confirm this. So again here m is the coefficient of dx, which is 1 over y minus 2 over x, and n is the coefficient of dy, which is minus x over y square plus 3 over y. Let us differentiate m partially with respect to y. We get minus 1 over y square. And now to differentiate n partially with respect to x, we get minus 1 over y square. From these two results, we can see that my is equal to nx. So it confirms that 2 is exact. Now we can use the formula for the solution of this differential equation, that integration of m with respect to x keeping y as constant plus integration of those terms of n which are free from x. Dy is equal to c. Let us put values. The value of m, that is 1 over y minus 2 over x dx, keeping y as constant, plus let us put those terms of n which are free from x. So we can see there is only one term with no x. So we can write 3 by y. Dy is equal to c. Now if we further simplify this, we get that integration of 1 over y, but 1 over y will be considered as a constant. So we have x over y here. Now integration of 2 over x, taking minus 2 as common, integration of 1 over x is ln x plus taking 3 as common, and integration of 1 over y with respect to y is ln y is equal to c. And that is the required solution for this problem. Let us study the last rule. If m dx plus n dy is equal to 0 is of the form y f of xy dx plus x g of xy dy is equal to 0, and xm minus y n is not equal to 0, then integrating factor for this problem is given by f is equal to xm minus yn. That will be the required integrating factor for this problem. To solve question number 4, it is easy to confirm that my is not equal to nx, which means that equation number 1 is not exact. Now we can see that equation number 1 is of the form y f of xy into dx plus x g of xy into dy is equal to 0. So we have to find xm minus yn. Let us multiply m with x and n with y. We get x square y square plus 2x cube y cube minus x square y square plus x cube y cube. If we simplify this, we get 3x cube y cube, and we can see that this is not equal to 0. So equation 1 is of the form 2, and xm minus yn is not equal to 0. Therefore, integrating factor for this problem is f is equal to 1 over xm minus yn, which is equal to 1 over 3x cube y cube. Let us multiply equation 1 with integrating factor. So if I multiply 1 with integrating factor, which is 1 over 3x cube y cube, this implies that we can get 1 over x square y plus 2 over x dx plus 1 over xy square minus 1 over y dy is equal to 0. And now you can easily confirm that the coefficient of dx, which is m, if you differentiate m with respect to y and n with respect to x, n is the coefficient of dy, they must be equal. So we can say that equation number 3 is exact. So we can use the method integrating m with respect to x, keeping y as constant. plus integrating those terms of n which are free from x into dy is equal to c. Let us put values in this formula. So we get the value of m here is 1 over x square y plus 2 over x into dx plus, let us find those terms of n which are free from x. So there is only one term which is minus 1 over y dy is equal to c. Now let us integrate this. In the first integral, y will be considered as a constant. So we have, taking 1 over y as common from here, if I take 1 over y as common, so I have x power minus 2. So we have x power minus 2 plus 1 divided by minus 2 plus 1. So we have minus 1 over xy from the first term. Let me write this term once again. There is some confusion. Okay, so let me write that term once again. From the first I have minus 1 over xy. In the second term, taking 2 as common, and integration of 1 over x is ln x. So I can write 2 ln x. Here taking minus as common, and integration of 1 over y with respect to y is ln y is equal to c. And that is the required solution for this problem. That's all.